In this video, we're going to do a few more practice problems related to intermolecular forces and properties. So let's try this one here. Propanol and propane are two organic molecules. Based on the structure and your knowledge of intermolecular forces, predict which one will likely have a higher boiling point. And so I put some guiding questions here to help you determine that. And you want to try to think about this in your head every time you answer a question like this. So first of all, do they experience LDF? And yes, they do. They both experience LDF. Are they isoelectronic to each other? Essentially, do they have the same number of electrons? How do we know that? You can just take care of the number of atoms that they have. And if they have the same number of atoms, then they probably have the same number of electrons unless there's a charge on one of them, but there's not. So let's just see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 atoms here. And here we have 1, 2, 3, 4, because there's 3 hydrogens, 5, 6, 7, 8, 9, 10, 11, 12. So these are isoelectronic. Yes, they are. Same number of atoms, same number of electrons. So what that means is that their LDF is probably on a comparable level, same amount of LDF. Do they experience dipole-dipole? Well, are they polar, in other words? So they are polar. If you look here, you have this OH over here, and here you have this CO bond over here. So that's a polar bond. I just want to clarify, this is not a bond between O and H. This is a bond, if you were to expand this, you don't know this yet, but if you were to expand this, the C can only have 4 bonds. So 3 of the H's are connected to it there, and then you have the O over here, and the same idea here. So it's definitely, this is polar, and so is this. So we have 2 polar molecules, so they can both do dipole-dipole. Okay, so does one molecule have more dipole-dipole, stronger dipole-dipole interactions than the other? So we have a situation here where they have similar LDF. So the LDF probably won't help us to determine their, which one has a higher boiling point or lower boiling point. But they do have differences, and they also have similar. They're also both similar in the fact that they are polar, and they have dipole-dipole. So now we have to find a difference between them to make our prediction. And if you look carefully, you'll see this one has an OH group specifically. And so since that one has an OH group, chances are that propanol would have a stronger dipole-dipole. It can do some hydrogen bonding. So based on this, you can make your prediction essentially saying propanol will have the higher boiling point. Why is that? Well, they both have the same amount of LDF. They're both polar and can do dipole-dipole, but propanol has an OH group, which allows it to do hydrogen bonding, which is stronger overall in terms of intermolecular force, therefore giving it a higher boiling point. So these are some questions you had to think about as you had to answer this question here. So these are guiding questions that you can use to assist you to answer questions such as this. So our next question is, a student claims that the difference in boiling point between the compounds below is due to LDF. Do you agree? If not, explain why you disagree by refuting the claim and then correctly explaining the difference in boiling points for the molecules. So these are the molecules shown here. And the student's saying that the difference in boiling points that you see here is due to the LDF. And so you need to first of all say if you agree or disagree. That's your first part to this. So you can pause the video, but even though you might think this is opinion, it's not really an opinion. There's a factual answer to this. You should really be saying you disagree with this statement. I disagree with the student. And you can say the molecules have similar masses, so they have similar LDF. So I can see that from over here. They have similar masses, so they have similar LDF, so it can't be the difference. So what is the difference? Well, H2O and NH3, ammonia, are polar, while methane, CH4, is nonpolar. This means that H2O and then H3 can LDF, and you'll notice here H bond, but CH4 can only LDF. So that's why the water and ammonia would have a higher boiling point than methane. So you've explained that you disagree, why you disagree. Now we're explaining sort of the main reason why there's a difference, and we said it's due to polarity, which is due to forces. The last part I would explain is why water has a higher boiling point than ammonia, because they can both hydrogen bond. You can say that the H bond in water is stronger than in ammonia because the OH is more polar than NH. And so that we know from the electronegativity difference. We can try out this problem over here. Predict which one would have a higher boiling point, ethanol or methanol, and justify your prediction. So again, try to pause the video and try it yourself. If you predicted that this one would have a higher boiling point, you are correct. The main reasons is they can both hydrogen bond to the same degree because of the OH group. So it's probably not going to be what's explaining their difference. What will be the difference is that ethanol is larger and therefore has more LDF than methanol. So you predict first, you explain a similarity that likely won't explain their difference, and then you tell me what difference does explain their difference. And this is a good question here. It's a nice challenge. So I want you to try it out yourself, but what I want you to get is that here we have a double bond, and you'll learn more about this later, but the double bond doesn't rotate. So these are two isolated molecules. If this was a single bond here and I drew it like this, I mean, actually I wouldn't be able to because you'd be missing atoms. But with a double bond, this is a molecule that won't rotate, and this is a molecule that won't rotate. And so you need to figure out polarity, and the big hint is draw the dipoles. So if you draw dipoles here and here after you do the bonds, and here, you'll notice that even though this molecule is made up of the same atoms, that one of them is actually polar and one of them is nonpolar. And so you might guess over here, well, look, it looks like these arrows are canceling each other out. So this is a non-polar molecule. And this one over here, the arrows don't cancel each other out. So you got some partial negatives here and partial positive end over here. So this makes this a polar molecule. So it's a bit of a challenging one, but it's interesting to try it out just to see. So now that you see polar versus non-polar, you can predict that this one here probably has the higher boiling point since it's polar, and therefore has dipole-dipole plus LDF. Whereas this one here, only LDF. And of course, you would write it in words with a sentence, as we modeled in previous questions, but that's the approach you would have to take. So at this point, you've done a lot of practice problems, and you're in a good position to explain a lot of the trends and properties that we've seen. So if I give you a table like this, you'll be able to explain a lot of the data that's here. So for example, if we look here, you'll see this is C6H12. And then here we have C5H12 and also C5H12. you'll notice there's differences in their boiling point. You'll be able to spot which one has why that is based on intermolecular forces. This one has a higher boiling point because you'll notice it has a different shape than these ones here. So they all have only London dispersion, but this one being more linear compared to branched or spherical had a higher boiling point because it has more surface area. So you can explain that data now. Here you can take a look at this and say, okay, this is a higher boiling point than this one. Well, notice this has an OH group and this doesn't. So you can say, well, okay, they both have LDF. They're both polar, so there's both dipole-dipole, but this one here is probably hydrogen bonding. And that one was just dipole-dipole. So the hydrogen bonding leads to a higher boiling point overall. Here you can see, you can make predictions. You can probably rank these from highest to lowest boiling point, or lowest to highest. Doesn't really matter. So by looking at this, you'll probably say this has the highest boiling point, this has the lowest, and this is somewhere in between. And if you predicted that, you're on the right path. And so you might say, well, they're similar sizes. They all have LDF, and there might be some slight differences in LDF, but it's probably not what's explaining the big differences in their boiling point. Here you could say, oh, there's no OH, hydrogen bonding. This is a polar molecule, but no OH, no NH, no HF, so probably just dipole-dipole. And this is nonpolar, so probably just London dispersion. And essentially with your knowledge now, you can explain a lot of data, you can make a lot of predictions based on the structure and polarity of different molecules that we've seen so far.